Long is coming in.
We only met him once. I mean, if you wanna-
If you wanna go there for a minute.
Okay. Cool. So, welcome. Today is our first paper reading class. I'm sure you all are tired of hearing me speak, so we'll have some of your classmates present on these two papers. I think they're both very cool papers. One of them is 20 years old and it's still cool, so I think that speaks to a good paper. So yeah, I'll let both teams present. Maybe we can use my computer so we can record everything and unless you don't want to be recorded, let me know. But yeah, team one, maybe you want to go first?
We're missing two.
We're missing two. Okay, team two, are you all here? You all have four, five, four. Okay. There's three of you, and you're missing the fourth person. Ah.
We can go for
You can
it.
go and try to interpret
Yeah.
the slides. And yeah, we ran through.
We ran it, yes.
Oh, okay.
Well,
Maybe
we
they'll
put
just
four of us and then we have one
maybe they
person
just
not.
ran into traffic or something. Okay. Do you think you'll be able to
We
keep
can
going?
give it a shot.
Okay.
I
Or
think-
you can, if there's their slide, you can skip over it and see if they
Okay.
come in. And,
Yeah, that's fine.
or
We'll make an attempt to interpret, but
I don't see anyone on Zoom.
yeah, the notes
Yeah.
are on the
I
laptop.
think we pretty much have like the overview, the experiment and the appreciation.
Okay.
And then,
Yeah, I
like the-
think we have most of it. Who else is walking through the door? No.
Okay.
Okay. We're just gonna go for it. If you can do the. Oh, okay, Hayden's here. We're missing one.
Who's the last?
Nawaf. We're just gonna go for it. If Nawaf comes in a little late. then-
Yeah, he was.
Yeah, he
She's
was.
there.
How do you click through this, by the way?
Oh, if you can probably right arrow.
No.
Oh, you can't. You can click this button and it'll go through.
Oh,
the-
I see. Okay.
Yeah.
You want me to do the
Okay.
click guy?
We'll go through it because no op section is a little later. So, okay, hello everyone. The paper that we looked at is called Codes RVPF, a raw localized particle filter for 60 object pose tracking. Next slide.
It's up to you. If
Is it-
everyone can see, then it's fine.
Later.
I think we can see pretty good. Oh, there we go.
Okay, great. So this paper was a collaboration between NVIDIA, the University of Illinois, Stanford, and UW. And so the goal of this paper was to estimate 60 poses of objects from images. So to kind of define what 6D means, 6D refers to 6 degrees of freedom. So if you imagine that you have an object, it can move forward and backward, left, right, and then also up and down across the 3 axes. But it can also rotate along each of those axes. So roll, pitch, and yaw. And so the goal here was kind of to be able to estimate the 6D pose of an object, which can be helpful for planning as well as obstacle avoidance. And so the traditional approach that other papers or research have taken is to match images with featured or pre-generated templates. So if their main observation is an image of something that they're looking at, it's kind of taking what they see in the image and matching it with something else. The problem with that comes about when you're trying to look at time-related information. So if you're just looking at the current image compared to templates, you don't really know what the previous state was. So you can't really make determinations based off that, which can be limiting for certain types of planning or sensing. The paper specifically calls out grasp planning, grabbing something as a challenge. And so the approach that this paper takes is to use a particle filter. Next slide, please. So the authors created something called CODES RVPF, which stands for like raw localized particle filter. And so in this case, a particle filter is being used to select a region of interest from the entire picture. So you have a whole picture. The particle filter is used to find the 3D translation and determine the size of an object in that picture. So kind of like going through the picture, finding a spot where the thing of interest is. And then once that is located, what happens is that it determines the embedding in the box. So embedding refers to, it's a computer vision term that represents like a numerical representation of that object or image. So calculating some number of that. And based off of that embedding value, that's used to kind of figure out rotation. And so for the sake of performance, the authors created, they pre-computed a code book to which they can match the embedding value to certain rotations. And so they do have the algorithm in there. It's a lot to look at, but if we go to the next slide, there's a figure in the paper that kind of describes this a little better. So, if you think with our previous step and with our current step, they have our current observation and they also have previous translation and rotation. And they use this information to select regions of interest. I think they're looking at like the mustard bottle that's in here. And then for those regions, they calculate the embedding value using their autoencoder. That is used along with a codebook to compute weights and also update orientation information about where the object's located and its rotation. And then it keeps going through the end of that step.
Any questions? Does it make sense? Because this is pretty different from how the particle filtering we did so far, right? We just got laser beams. So, yeah, you all should ask questions and give them a hard time.
Explain further what exactly the embedding value is and what it corresponds to.
Yeah, I don't know a ton about the computer vision side of things, but I think the idea is that if we're looking at our picture here, first we kind of select a region of interest, and then we have, if we're looking at the mustard bottle, for example, there's some way to encode like a value based off of what it looks like in this picture. And so based on that value, which is kind of, you know, turn the pixels into some kind of numerical value, they can cross-check that number with basically a code book that's like, if it looks kind of like this, it's probably in this rotation. Or if it looks kind of like this other thing, then it's maybe in the other rotation.
The autoencoder uses the image to encode it down to actual code. And then the code book is just a ton of images that have been translated down and stored at different poses, somewhere around like 200,000 per image. So it can then use those, match it together, and whatever's closest gets the highest probability.
You can think of the autoencoder as a factor, but it's hard to compare pixels, right? So you have like, because you in an image, you're never going to get exactly the same image again. So if you compare literally pixels, you're never going to get anywhere. And like you shift something off by one, the pixels are way off, but the images are not way off. So the autoencoders try to like essentially do compression. So they try to take your images, compress them down into vectors that are easier for the sake of things like comparison. And all that autoencoders try to do is they try to encode images in a way that allows for reconstruction. You like encode and then reconstruct. And the idea is that an autoencoder feature, the C's, are like a vector that capture the most important parts. So if you like know how PCA works, it's like dimensionality reduction. So it's trying to take these images and reduce it to like the most salient. And then you compare the same images. And the argument is that the things that reconstruct the images are the most salient parts. And then the code book, you can almost think of it like a softmax. So you take your region of interest, you encode it, and then you compare it against all the possible things that it could be, and each of them gives you an unnormalized weight. You normalize it and it gives you a probability distribution of similarity.
Cool. All right, I can handle it.
You got it.
Yeah, thanks. So I'll be going over the experiments that were conducted using the POSE RBPF. It was tested on 2 separate data sets, which are just images. Yeah.
Why is it called RBP? Like, what is Rao platform?
It's the
So I have-
two.
Yeah, I have that actually in a further slide
Okay.
for our
like-
appreciation,
yeah.
but yeah, I go through it a little more in detail, what that process is.
Cool. Okay, so it was tested on 2 different data sets, which are just sets of images. The first one was the YCB video data set, which stands for the Yale CMU Berkeley Object and Model Set. Consists of 21 objects in red, green, blue that also have depth. The objects are a mix of textured and textureless, and they're measured with 2 metrics, the ADD and the ADDS. The ADD is the average distance between the corresponding 3D points on the object's actual pose versus its predicted pose. And the ADDS is the average distance between the closest point between the 3D model of the object's actual pose versus the predicted pose. This is basically just used for symmetric objects. It works better. The other data set was the T-less data set, which stands for textureless. It's 30 non-textured objects in red, green, blue, and that contain depth. So this is the like a graph of the data results of the YCB video data set. And kind of how this works is the chart shows how POSE RBPF performs against a couple other different methods of pose estimation. to include post-CNN, dense fusion, and dope. The results are broken up into red, green, blue in that blue box. And then the images with the depth is in the fuchsia box, I guess. The bolded results are the best performing. So as you can see, going for like the first line there, the 002 Master Chef can, we can see all the way at the end of the blue box, our Pose RBPF++, which is like a hybrid version of Pose RBPF. It performed the best. It doesn't always perform the best in every instance, but if you look at the bottom over the last row where it says all for RGB and RGBD, the Pose RBPF outperforms all the other models on average. For the second data set, the textureless, same thing. You can see where the best performing model came in. It was going up against data with GT2D BBs, which is actually ground truth two-dimensional bounding boxes. So that's just like a box drawn around the image. The last column does not have that, but if you look at all the data at the bottom, the Pose RBPF model outperforms the others, the SSD and the Retina Net and all that stuff.
So conceptually, like what is different about both RBPF and Retina Net? What's the magic sauce?
I am not exactly sure.
I think it goes back to like, it's comparing a new way of looking at finding 60 pose of objects instead of the traditional format of matching, but I don't know the specifics on the different technologies it's compared to.
Something to mention in the last slide on the YCB video data set, they were compared against post-CNN and DOPE, which are pose estimation models that are different than ours. But the three columns to the right of the RGB, they contain Pose RBPF with 50 particles, and then the next one is 200 particles, and then the last one, like I said, is a hybrid model. So the more particles, the more accurate our model gets.
You know what the main distinctions in the hybrid model are? How it's different?
Yeah, the hybrid model is actually, it just contains like half of its particles from post-CNN, which I can't explain very well, and then half of its particles from previous measurements. So it's taking like a T-1 measurement, incorporating that. Yeah. Actually, do you guys know that?
So the YCB is a put together data set, which tons of different poses and things like that, that are put together from Yale, Berkeley, and somewhere else.
CMU.
CMU.
Yeah, so that is asymmetric objects and things like that in certain positions, right? So they use that as a data set that's already available. The textureless basically has to do with how it's encoded. And some of those textureless objects are symmetric. So if you have it facing this way versus facing this way, you still have to determine which angle it's actually in. And so by using the two different data sets, you can see basically that it works in symmetric and asymmetric objects.
So just look at dope. So I think dope is basically a method for pose estimation using the CNN, which doesn't use filter. So
Okay.
like it basically just uses simulated data with an RNN, it doesn't explicitly propagate uncertainty.
Okay.
It just like uses lots of simulated data and tries to directly predict where the uncertainty. I think the point of the comparison with dope is to show that it's filtering and the maintenance of uncertainty and propagating it probabilistically is filtering.
Okay.
Interesting.
Cool. I'll move it on to related work.
Sorry, one more thing. Maybe one way to think about this, the way you should read these papers is they're going to throw huge tables at you, and they usually like obviously your method is better, so like they're not really that helpful. The way that I read them is try to look for which pieces of the method are super important. So like for instance, if you go back to your table, right? You like try to look at the delta between Pose RBPF and the other methods. Like, is it the features? Is it the filtering? Is it the architecture? Right? And like that kind of tells you what to take away, because usually everyone's going to self-select for their method. Like that's not that helpful. But like if you can see which elements matter, that's way more.
Okay.
Basically, like you were saying before, like this one is using particle filtering, this one's
Yeah.
not, and that makes it.
Yeah, exactly. Like everyone's gonna lie about their paper.
Yeah.
So I'm not saying that this paper is, so I'm saying you have a tendency to try harder on your method. But if you like look at the ablations, often they're going to be really impactful in telling you which things.
Cool.
At least that's how I think.
Great.
Yeah, so as Jaden was talking about, the traditional methods before this paper is pointing to is basically you would extract features from objects in different orientations and you map them. And then a more modern approach would be using a convolutional neural network like PostCNN. So it would do 2D object detection, and then on top of that, it'll run pose estimation. But then, as we were talking about earlier, the downside of that is that there's no previous state. So there's a lot of like flickering where the object will, if you're trying to track it in a video, it'll flicker between different poses, when obviously that's not possible in real life. So having that previous state is really helpful. And then an interesting project I found was there's something called foundation pose, which what was interesting about it is apparently they generated all of their data sets using ChatGPT, and the texture they overlaid on all the 3D models was generated as well, I think by Delta3. So that was pretty interesting. But also that one is able to, you just give it either a CAD model or just a few reference images of any object, and then it can estimate pose in the level scene. You don't need to, like there's a lot less setup required. And then there's this other paper I found that looks like it has improved accuracy on textureless objects, although I'm not exactly sure how that was accomplished.
This is Nawaf's slide.
We can go
I don't
through some
know.
fishy shows up.
Skip it and
We'll
Should I
skip it
come back?
for now, and then we'll.
Okay.
Okay.
I'll see if he sends something on Discord.
Okay, let's keep going for now, I suppose. So, over here.
So a couple of the things that we think that they did really well in this paper. One of them was they were very thorough in their explanation for what formulas they used, what kind of probability formulas in order to generate their results. All the experiments were done in a way that if you had any doubts on this paper, you could go back, implement these formulas and rerun these tests, and should come up with pretty much the same results. So we thought that was pretty good.
Did they release code?
What's that?
Did they release code?
No, but they have all of the formulas that you could, wow,
Formula and code are different.
that's true. It's true. I agree. But if you are looking into this and want to prove them wrong, I would imagine you have a little bit of background in this and could probably come up with it at least fairly close anyways. Yep.
You who is super motivated to do it. Extra credit.
The other thing we like is in the experiments, as you saw from the tables, a lot of the categories showed that this was a better method, but some of them didn't. And I appreciate that because, you know, like you said before, a lot of these things are going to show how theirs is the best and everything, but it did show some truthful data showing that there were a few cases where this was not the better method. The other thing too, I thought I added that on here. They showed a lot of images of the process. So one of the processes they do when they're doing the particle filtering or after the particle filtering before they send it into the encoder is it generates a synthetic image to remove any occlusions, because this is meant to work with occlusions and in weird angles and things like that. So it would generate a synthetic image that it would then send into the auto encoder. And one of the things that they did was show how theirs was and a couple leading methods up to this point, and it showed how much better theirs actually was. Yeah, so there you go right there. That's the image. Apparently I should put on the last one. So a couple of the key learnings, the things that we kind of thought were important were, one, what is Raoul Blackwell's filtering? The other one is how it was used in this context. And the third is basically once they go through the auto encoding, how do they use that data to do anything like special? So the first one, what is Raoul Blackwell as filtering? Basically, it uses a two-step process. The first step is particle filtering to find the region of interest and do the object translation to generate the synthetic image. The second part is once they have send it through the autoencoder, they get their code out and they actually do hard processing of the data not in a, I guess, not in a probabilistic model, but kind of in a direct model of what is the closest thing that is showing up in this. And it is a probability scale overall, but basically instead of using a particle filter that could take time and complexity, this is a very straightforward data analysis comparison, which takes a lot less time. So that's what makes this so cool. So how they did it in this one, or how they use it in this one, is they basically took an image of something, and the filtering or the different particles is different sections of the image. And once they found the object and performed the object translation, that then went into an encoder, matched everything up as it should, and came out with basically the most likely pose that this object was sitting in from the region of interest. Let's see.
Is it just,
Yeah.
is it just props? Like, shouldn't the particles be full folded?
So basically what it does, and they have a couple pictures on there, and I probably should have added it, but it actually takes the particles as basically cropped little images on there. And then it comes up with the object, or in the process of doing the object translation, it goes through a probability mapping, and it finds that object based on that algorithm that they use for the object's translation. So once they have that object translations, they develop a synthetic image like this, which, as you can see, these are the leading methods up to this point. So this one, you can kind of barely tell where it's at. Same with this one, you can kind of see, where it is and kind of what orientation it is, but if you had to guess that to a certain degree, there'd be some noise there, whereas this one is much more clear and easier to kind of translate.
I guess one note on Rao localization is there's a pretty fundamental result in statistics called the Rao theorem. And it says that if you have an estimator, which kind of estimates some quantity, and you condition your estimator on some sufficient statistics of your data, then that estimator is strictly more accurate. So they're arguing that they have translation and rotation. They do this separation. So they first try to estimate translation, then they try to estimate rotation condition. And so that the estimation of one is now conditioned on the sufficient statistic of the other.
Yeah.
And that makes everything more accurate. That's the Rao localization is a general statistical theorem, and it just says that estimators on sufficient statistics are better. And here this factorization of their prediction is what is their implementation of Rao.
Okay. Perfect.
Right.
So some follow-up work. There's other papers that cited this one. So one of them is called Six Pack. And what I got out of it is that they were able to just given a video, you don't need any previous input. You don't even need pictures or it'll watch the object as it rotates and will accumulate the known features over time. And I can do that in real time. And then this other one is CAPTRA, which is able to track the pose of individual segments of an articulated object. Like the example they're using there is a laptop. It can track both the screen of the laptop and the lower half of the laptop. And then this other one, RelPose, was able to output relative pose instead of absolute pose. So I think you would give it two images of an object, and it could tell you how it changed.
I think that's everything, minus limitations, but
We can go back through the limitations. and
we
try-
can try to do the
Right,
limitations if you want.
Well, you all.
Yeah.
Do we,
Yeah.
do we know any?
Well, we can.
I can.
Tell us why this is garbage.
So, basically, one of the things I was reading through, when we were going through the occlusions is they do have a failure rate if it's too covered up. So if it's less than 65% covered up, usually the object translation can still figure out what it is and develop that synthetic image. But if it's over 65%, there's a pretty good chance that it's going to fail in determining what object you're trying to translate. And you can see that kind of on the graph there. Not 100%, because I haven't gone through the slide yet, but yeah, so you can see basically it's more accurate in determining at the lower occlusions.
I think it's just saying that you're training on simulation data.
Yeah, yeah.
And you apply to real world data, so other encoder, et cetera, it's trained on sim data, and you throw real data at it, it needs to be fixed.
Yes.
Though, like relating it to concepts from the class, it's the same problem as model specification. It's like the observation model is now, or your feature encoder is now. There's some gaps.
Yeah, I remember something about the wood block having an issue because in real life, it's like the wood grain's gonna look different.
There's two other comments. One is they didn't give code, and two is they gave a video, but there was no voice over anything. It was just like a video panning through a couple slides. So it wasn't very helpful.
Alright, so maybe a question for the audience, what did you like and what did you not like about the filter? Or, yeah,
Does it make
did not
sense?
that, yeah. Or did it like, it was just, did not strike up any emotion?
Oh, it was so perfect. That you had it.
Yeah.
Congratulate you on perfect. Who do you use it in your, daily filtering?
As long as we're using snapshots, I think it worked great.
So this paper is from like, what, 4 years ago? Maybe 3 years ago? It's like maybe, the features that we have are way better now than they used to be. So you don't have to use autoencoders, you can use self-supervised learning, other types of features. And so if I was to rewrite this paper today, I would do that.
Well, even like machine learning stuff is way better now than it was 5 years ago.
Right. And so the main place this guy is using machine learning is just in the feature learning. And so that's what this.
You have a question?
I was just gonna say, I'd like to know how it performs outside their data sets, but it's super random picture and experience.
Probably wouldn't, because the main thing is it would need to be loaded in order for it to develop like a likelihood of it being posed in that certain way. Like I said, there's a picture in there, it's like a figure in there, where it shows like 10 different angles, but it says that each object could have up to 200,000 different angles so that you're more precise at which, how likely it is to be in that exact position. So like if you loaded into your data set, I'm sure it'd work fine.
Like if we were to implement it, it seemed like a pretty complex process enough. Featureization, outlining, all that stuff. Would it be computational? You did read real time.
I think it is kind of a
Yes.
code book, right?
Yeah.
If you compute.
Yeah,
the-
because of the Rao-Blackwell's algorithms and theorems that it uses. So it breaks down the complexity. So if you were trying to do this in particle filtering, like the whole thing, you're talking about a lot of processes running. But since you're only doing a particle filtering on one step, the next step is just data analysis. And so that data analysis takes way less time. There's no sensor readings or anything like that coming in. It's just determining, what poses. So by doing that, it cuts it by quite a bit.
I'm forgetting if it was this paper or one of the other ones I looked at, but I thought they said it could run at 20 FPS.
Yeah, it can. Yeah, I think the more particles though, the slower it runs. I think is what it said.
So one last question, so we have.
I think there's.
Okay.
So like, did they compare like their autoencoder and all like any more so like old school, like sort of feature abstraction approaches?
Well, I think that's what the
The chart,
CNN and
these guys,
Those were
Yeah, the
not
post
as old
CNN.
as the-
yeah, they're not super.
They're like, those were like the kind of state of the art.
Yeah, they're just techniques from like 23 years ago, you have to use sort of like common plugins for ADA such sort of abstract sort of features and use that. Let's make it flows. I was like, what did I say actually? Ran analysis on
Yeah.
Yeah.
I don't know.
I don't know that they did analysis on it because I think one of the major things they were saying is that like, because you can take in like this previous step of translation and rotation and their method, that makes it automatically improved because their purpose is to use previous like temporal information so that they can do planning better. So I think because they're trying to do it in the context of doing other things, they probably didn't compare it to papers that don't have the ability to do temporal calculations.
Okay, let's put it over again.
Quickly, do you wanna come up with something?
I have to say, I think the vetting helps someone understand it.
Yeah, yeah, trust me, I know. You all emailed it to me recently, right? Is the one, do something, do you need speaker notes? Or you good? Do you need speaker notes or no?
Oh, no.
Okay.
At least I don't.
Let's see. I think we can. No problem.
Should I try to like rush through it a little bit because we're only like 18 minutes, right?
Okay, don't worry.
Okay.
Um,
Good to go. Yeah, so hi everyone. We're Team Top Gear, and the paper we're presenting today is on KLD sampling, which can sort of be thought of like an extension of sort of normal particle filtering with resampling. So the overall premise of sort of KLD sampling, or I guess the key idea is the size of a particle filter sample set can be set in order to sort of bound the sampling error while still like having as small of a sample set as possible. In more detail, what that looks like is if we assume the true posterior is given by a discrete piecewise constant distribution, which more on that assumption later, we can set the sample size n such that the distance between the MLE estimate based on sort of the observed data and the true posterior does not exceed some threshold epsilon. And the distance in this case between the MLE and true posterior is given by the Kolbeck-Liebler divergence, which is actually where the KLD acronym actually comes from in this paper. That's given by this formula here. So as for the method, so before we get to the derivation for the setup,
Can you tell us what the field is?
yeah. So
Like what?
I mean-
What is it kind of included?
yeah, so it's basically a way to measure sort of how different two sort of distributions are, right? Two random variables. Yeah, and this is given here, and I guess you can sort of interpret it as almost like the expected value of like p of x over q log p of x over qx given p of x. So this paper calls it a distance. There's some criticism there because A is not symmetric and B can actually be negative, which is not really something you want for a distance. So okay, not.
Scale divergence can never be negative, the log P over Q can be negative,
Yeah.
but scale divergence can be.
Oh, okay. So yeah, for the sampling setup, so suppose n samples are drawn from a discrete distribution of k different bins, which we can sort of express this vector x here. So like let x be a vector of size k, denote the number of samples drawn from each bin. So basically x of 1 would just be like the number of samples that are in bin 1, x of k would be number of samples in bin k, so on. And x in this case is distributed as a multinomial variable here with a probability p here, which represents the probability of each bit, which potentially represents probability of like drawing basically a sample into each bin here, right? So p of 1 would be the probability of like a sample going in the bin 1, p of k would be probably a sample goes in the bin k, and so on. And the MLE of p is sort of given by this here, which is just basically weighting each bin by basically the total here. So basically you take each bin, make sure it sums up to 1. That's actually the MLE, which gives that the actual probability vector here.
But maybe let's slow down a little bit, right? Like,
Mhm.
okay, so why are we doing all of this? We're trying to decide how many samples should we have in the part. That's all we want, right? We want to decide, okay, we chose some number of samples n, like how do we pick it? And the reason we're using the KL divergence is the motivation is the KL divergence between the MLE estimate, which is like how good is your approximation to samples?
Mhm.
Like how different is that from the true distribution? And we want that to be like some number.
Yeah,
What's
less than
the
epsilon.
derivation you want to go over is just trying to estimate, like, derive that n for which like the sample estimate is a good approximation to the truth.
Mhm. Yeah. So the end result is we want basically like with probability 1 minus delta, basically be able to determine whether or not our KLD distance is gonna be less than epsilon. That's sort of gonna be the end
But
result
I
of
guess the
this.
point is that we took a real distribution, we approximated it with samples, right?
Mhm.
Or particles, if you want to. And that approximation is gonna be bad. And how bad it is depends on how many samples you.
Yeah.
So you want to get away with the minimum number of samples such that your approximation is at least some quality.
Mhm.
And that's kind of the premise. So even if you miss the rest of the details, just like a little bit.
So yeah, moving on to derivations. This is gonna be like a lot of math from here. So we sort of start with the actual likelihood ratio statistic for testing P, which is normally conventionally used to test, like, say, like some distribution against a null hypothesis. And that expands out to this like formula here. You can see it's sort of like all the way to the right here. And moving on from there,
Like we jumped over that whole thing at the rest. Like, what the hell is that? Like, at least tell us intuitively what is this thing? You introduce a lambda and then add or something. Like, what is going on?
yeah, so like overall, what this formula is basically trying to do is like measure some kind of assumption against a null hypothesis, right? Which,
So what is the null?
like in this case here, is this basically like our MLE versus our true distribution, which is kind
So
of
your
an odd
likelihood
setup.
is just trying to measure how different is p hat, which is approximation from your truth.
Yeah. Yeah, and so like moving forward, when P is a true distribution, the likelihood ratio actually converges to the chi-square distribution, right? Which comes from something called Wilks' theorem. Like the paper for this theorem is actually like longer in this paper. But sort of the end result, right, is that like the likelihood ratio actually converges to a random variable, which represents the sum of a bunch of squares, standard normal distributions. And since like it converges in this case, we're actually gonna use this like an assumption layer, so we will not have n equals infinity. That's just not possible.
So yeah, this paper is a bit long, but the important thing to remember is that if you're, can you go back to
Yep.
like if you one more,
Oh yeah.
like you have this like sum of things, and if you think of each thing as like a square Gaussian family, like it will a chi-square distribution is the sum of a bunch of squares. And so you can think of this thing as converging to like there's no point going through that theorem right now unless you're super interested, but like just think of it as like the scale divergence or likelihood ratio approximation goes to chi-square, and we'll use special properties of the chi-square to derive the number of samples.
So yeah, so we're using this theorem, and from the fact of the summation portion, the rightmost term figure 1, which is right here, it's actually just the KL distance, which in this paper is actually denoted as K of P and Q. We can actually get here that we can actually approximate. We can actually like approximate the probability of like whether the KDL distance here, right, is less than epsilon. It says whether or not the chi-ski. Wait, stuck. It says whether or not this sort of like chi-square distribution here is less than 2 on epsilon. And this is like and this paper also knows approximately equals, so we're just dot above the equal sign here. And the reason it's approximate is because once again, we do not have n equals infinity. So yeah, starting with the upper quartile of chi-square distribution, like, and what you can sort of think of like quantiles is we're basically dividing our probability space in a bunch of equal sized chunks of equal probability, right? And sort of definition of the upper quantile is given here. Or is this a probability of some arbitrary random variable, right? Which in this case is xk minus 1 squared. It's basically like less than basically our critical value, right? Which like say in this case, we basically just want to like have some random variable. We just want to like divide, say, like 1% chunks, right? The upper quartile here. I'm not explaining this well, but
So maybe one way to think about it, if you have a distribution, right, and your quantile is telling you like what is the probability that your value, like the probability, if you're looking for the like 10% quantile, it's the value for which like 10% of the probability mass lies above. Right? And so by definition of the quantile, like the probability or like lies below. And by definition of the quantile, like the delta quant or 1 minus delta quantile, the probability that something lies below it is 1 minus delta. Like that's the definition of the quantile. So there's no like math in that. That's literally what the definition of the quantile.
Yeah, sort of like using the equations from the previous slides here in this definition of the quantile here. We can set n such that 2n epsilon is actually equal to a separate quantile here, which is the critical point. And that yields that the probability that the distance between like the MLE and the true distribution is less than epsilon is 1 minus delta, or approximately equal in this case. And we can achieve this by setting n to equal to be 1/2 epsilon times the critical point. And finally, we can use the Yenner approximation in order to calculate this critical point, which is this whole mess of formula I'm not going to get into here. But the important thing is K is the observed number of bins with size delta, which we actually like calculate as we're sampling, basically how many bins do we actually need to actually bin our data. And Z sub 1 minus delta is actually the upper quartile of the standard normal distribution.
Yeah, so for the experiment part, they run the algorithm on this robot and do a whole about experiments. And I just want to give you some intuition why we are doing that. So at the beginning, we have a little bit of detection, right? So the uncertainty is pretty high. So therefore, the probability or the possible positions is all over the map over here. But once we detecting more, the kind of particle is collapsed into 4 over here and only 1 over here. So we need more samples on the beginning to kind of including all possible candidates, and therefore we kind of make sure we are including all the things. But later on, like it's kind of collapsed to certain data, so we don't need that much sample. Like like 1,000 sample or 100 sample, it's basically give the same thing or didn't lack much, didn't lack some generalities. So therefore, this algorithm is kind of adapting the number of samples rather than treat them constantly adapting it. So on the graph over here, you could see that passing the times, the number of sample is kind of changing through the time. So therefore, we don't have to cover how that's changing through the time, but we already derived to the equation we need. So later on, you could see that this the equation we derived before, right? And the main thing is we need some relationship between the n and k. So n is the number of samples, and the k is the number of bins with the sample in. So we cannot divide the whole space into multiple bins. And when you're doing the sample, right, some of the bins do have the particle in, some of them don't. So k is the number of bins with the sample in. Therefore, once the n is greater than the whole equation we derived before, we say that the KL distance is small enough. So our sample distribution is actually like good representation for the true distributions. So we are good to go. But the thing is, without really doing the sample, we cannot never know whether we reaching this relationship. So this doing the sampling, but doing step by step. So for each sampling iteration, they're checking the n and k numbers. If they reach the threshold, they just stop. But if not, they kind of adapting more particles by sampling again and checking this relationship. The same as the once the bin size is fixed, the k has the upper bound. Therefore, we make sure this code definitely terminates. So once it terminates, we are good to go. Good to go. And therefore, this is the result once they running that robot on this map and also including another two sampling algorithms. The first, our algorithm is kind of make sure the KL distance between our sample distribution and the true distribution as in some certain small values. Another one they including is fixed sample, which is we including in the lecture, like the number of particle is fixed through the time. Another one is the likelihood-based adaptance. So they're changing the number of samples, but changing by the landscape of the likelihood. So which is like sometimes one particle have high weight than all others. Sometimes like all the particles have equivalent weight. So they're changing that number, that sampling number by the likelihood landscape. So they compare the results. You can see like this one is the KL distance against the average number of samples. We can see that the KLD sampling is reaching the lowest or lowest KL distance by a small number of the samples, which is few cents. Since this distance is actually the differences between the true distribution and the oversampling distribution, right? And another graph over here is the error against the number of samples. So you could see a U shape over there. So does anyone know why the sampling is actually when we oversampling we got high error? Yeah, oversampling, but either oversampling is a good thing since we got multiple candidates.
Well, then we can, the probability is gonna be focused on one point, so it's really.
Yeah, kind of. The thing is, when we have multiple sampling where oversample, the update time is pretty high, right? So therefore, those information is already outdated, so it's not accurate anymore. So therefore, we got a bump up over there. So the thing is, KLD sampling is reaching the lowest error on here, but when they bump up, it's not too bad, right? It's almost the same with another two algorithms. So it's showing up the KLD sampling is good and have kind of using smaller resources, but get a smaller error, which is a good algorithms. And finally, there's a related one. So KLD distance
By
is
the way, you don't have to rush, like, I'll give you time at the start of my next lecture, so just go through it slowly and calmly and we can take more time, so don't worry, don't stress.
okay. So the related work part, so this KLD distance sampling is kind of created in 2001, and the particle filter which we covered in the lecture is kind of created by like 1980s. So at the 1990s, we just covered that. They kind of changing or adapting the number of samples by the likelihood landscape. We already covered that algorithm. So this algorithm is inspired by those two papers, which about like changing the number of samples by the likelihood. And then around like 2010-ish, the kind of the robot this KLB sampling is widely used by some robot simulations and some like real world React robots. So it's kind of used by like real world robots. And finally, other people like be writing a bunch of like localization algorithms and other kind of sampling algorithms, and they do compare their results to the KLDs. So I just including two of them, like I say at MCL and I say KLDs. So this one is actually the whole localization algorithm that's been just sampling algorithm, and this one I'm not pretty sure, but that's the kind of comparison between their results or between their particle distributions. Yeah, so some questions.
I think we might get it done, but would you all be okay doing it on Fridays? Just at the start of my lecture, we'll check out the things. Would that be okay?
Yeah.
So that all of you get to present, would that be okay? Sorry about that, this could be very kind of. But yeah, let's give them a big hand and we'll. So please do attend and. Thank you. Sorry to cut you guys off. We're gonna get kicked out in a second.
And
Yeah.
can you adjust with the normal, even if you were passing with the original